Hello, my name is Pedro Garcia, and this presentation is for my numerical methods final application project. The title of our project is Stormwater Detention Basin Outlet Design using RK4 and bisection. For the project, we applied two numerical methods from class to a civil engineering stormwater design problem. The two methods we used were the fourth order wrench coda, also known as RK4, and the bisection method. The engineering problem we studied was a stormwater detention basin that receives runoff during a 4-hour storm. Detention basins are important in civil engineering because they temporarily store stormwater and release it at a controlled rate. This helps reduce flooding and lowers the peak flow leaving the site. In this project, the goal is to determine the outlet pipe diameter needed to keep the maximum basin water depth at or below 2 meters. The basin was modeled using conservation of volume. The change in basin water depth depends on the difference between inflow and outflow divided by the basin surface area. The inflow was modeled as a triangular storm hydrograph. It starts at 0, rises to peak flow 2 cubic meters and per second at 1.5 hours, and then decreases back to 0 at 4 hours. The outflow was modeled using an orifice type equation where the discharge depends on the outlet area and the water depth in the basin. The first numerical method used was RK4. RK4 was chosen because the basin depth changes continuously over time, so the problem is naturally an ordinary differential equation. At each time step, RK4 estimates the slope 4 times and combines those slopes to calculate the next water depth. This makes it more accurate than a simple Euler method, which still being reasonable to code manually in math. The second numerical method was the bisection method. Bisection was used to find the outlet diameter that makes the maximum basin depth close to the 2-meter design limit. The function used for bisection was the maximum depth for a selected diameter minus the design depth limit. If the result was positive, that meant the basin was too deep and the outlet diameter was too small. If the result was negative, that meant the outlet diameter was large enough to keep the depth below the limit. For the MATLAB implementation, the code first defines the basin area, initial depth, design depth limit, discharge coefficient, gravity peak, inflow, storm duration, and time step. Then the code starts the bisection method using a lower diameter guess of 0.2 meters and an upper diameter guess of 0.8 meters. These guesses bracket the solution because the 0.2 meter diameter produced a maximum depth above 2 meters, while the 0.8 meter diameter produced a maximum depth below 2 meters. For each trial diameter, the code calls a custom basin dissimulation function. Inside that function, the water depth is solved using a manually coded RK4 loop. The code calculates inflow, outflow water depth, and maximum water depth during the storm. The maximum depth is then returned to the bisection method so the diameter can be adjusted. The code is extended beyond a basic RK4 example in a few ways. It included bisection, design logic, array storage for iteration history, diameter guesses, maximum depths, and errors. Also included diameter sweep from 0.2 meters to 0.8 meters to compare how outlet size affects maximum water depth. Finally, a time step verification was added using 120 second, 60 second, and 30-second time steps. Looking at the results, the storm flow hydrograph shows the triangular storm input. The inflow increases to the peak and then decreases back to 0. The basin depth graph shows that the water depth increases during the storm and reaches the maximum very close to the 2-meter design limit. After that, the depth begins to decrease because the inflow becomes smaller than the outflow. The inflow and outflow graph shows the inflow changes quickly because it is based on the storm hydrograph, while the outflow responds more gradually because it depends on the stored water depth in the basin. Even near the end of the storm, When inflow drops close to zero, the outflow is still positive because water is still draining from the basin. The diameter sweep graph supports the expected trend. Smaller outlet diameters cause larger maximum basin depths, while larger diameters reduce the maximum depth. For example, a 0.2 meter diameter produced a depth of 3.2 meters, while a 0.8 meter diameter produced a maximum depth of 0.93 meters. The graph crosses a 2 meter design limit near 0.49 meters, which matches the bisection result. The bisection method found a final outlet diameter of 0.489 meters, or about 49 centimeters, with this diameter, the maximum water depth was around 2 meters, which is just below the 2 meter design. The final depth error was only negative 0.00360 meters, so the design met the selected tolerance. The time step verification also supported the accuracy of the RK4 solution using the steps of 120 seconds, 60 seconds, and 30 seconds gave almost the same maximum depth. This showed that the selected 60-second time step was small enough for the project, and that reducing the time step further would not significantly change the result. There are still possible sources of error. Because the model is simplified, the basin surface was assumed constant, but real basins often have slope sides and changed surface area. The storm inflow was simplified as a triangular hydrograph instead of using real rainfall runoff data. The outlet equation also does not include every possible hydraulic effect, such as infiltration, evaporation, clogging, sediment buildup, tailwater effects, or additional pipe losses. In conclusion, the project showed how numerical methods can be used for a practical engineering design problem. RK4 is used to simulate the basin water depth over time, and bisection was used to solve for the required outlet diameter. The final diameter of 0.489 meters kept the maximum basin depth just below the 2 meter limit. The results supported the original hypothesis that smaller diameters increase maximum basin depth and larger diameters reduce it. Future extensions could include using a real rainfall hydrograph, modeling a basin with changing surface area, adding infiltration losses, testing different storm return periods, and emergency spillway, or including emergency spillway. That includes my presentation. Thank you.